All right. So now can you see the screen? Is it visible?
Yes, sir.
Visible is it?
Yes, sir. Yes.
Okay. So what we have done, we have actually arrived at this point, right? At this point, okay. That means the complete block diagram transfer function of the load frequency control system, okay, including the generator, load, governor, and turbine. Okay, and this is the complete transfer function. Input is the speed changer position of the governor, okay, through which we can give power increase or power decrease command. And the another input is obviously the change in load. That is obviously it will be done randomly by user of the by the consumer. There will be switch on or there will be switch up the load, and because of that there will be change in frequency, and frequency change is feedback given as feedback input to the governor, and this is how the system works. Okay, so the complete block diagram, each component we have discussed earlier, and let us now analyze and let us now see what happens. Let us obtain the value of del f. Okay, how the frequency changes if the demand is varied. Okay, then let us see. So speed changer, for the time being, let us assume that speed changer is kept at the fixed position. That means we are not moving, giving any input to the speed changer. No external input is given. There are changes in demand, and as response to that, frequency will vary. And since the frequency is varying, let us find out the expression of frequency in terms of change in input and change in demand. Okay, so if you write the expression for del phase, it is kp by 1 plus stp into del pgs minus del pds. There is a minus sign here, there is plus sign, and del pgs minus del pds. Again, you put the value of delta pgs. How much is delta pgs? Delta pgs is delta pcs minus del fs by r. That, sorry, into 1 by 1 plus stt, 1 by 1 plus stg into delta pcs minus 1 of del fs by r. Okay, so this is how the value of delta fs you can find out, and you simplify then and find the expression for del fs. Now you see that what we have done, we have actually not given any input to the through the speed changer. So what we have done, speed changer position we have kept unchanged. So as a result of that, you can say that del phase ultimately will be like this in terms of delta PD. So since del phase, del PGS, it has been del PCS basically has been made zero, because since there is no change in the position of the speed changer, any change in generation will be due to change in frequency only. And if you find the expression finally, it will be like this. Okay, you do the manipulation, you verify whether there may are some actually typing errors are here. So those errors you find out, and you can, I think you can rectify that also. So del FS expression will be like this. It is somewhat long expression, okay, but let us find out the expression and see how the frequency changes in response to change in power demand. Now you see that we are particularly interested about the final change in frequency, because finally what frequency becomes after a demand is changed, after a variation in demand is made, that is important to us. Okay, so steady state frequency variation following change in demand. That means a change in demand has been taken place, some load has been switched on or off, and we have not changed the position of the speed changer. Now we want to find how much the frequency will change at steady state after the change in demand. So if this is the expression for delay phase, to find out the static or steady state change in frequency, again you can employ the what we call, that means the final value theorem, where we find out the value of s times delta fs, s times delta fs, as s is made or as you approach towards 0. So limit s tending towards 0, s time del fs, you find out the value. So if you do it, you will be multiplying this by s, this s and this s will be cancelled out, and put all other s to 0. This will be 0, this will be 0, this is 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 0. So finally you will be getting this expression, minus delta pd into kp by kp plus r by r. That means you can rearrange it, 1 plus kp by r, 1 plus kp by r minus delta pd into kp. The delta pd is the value of the uh, variation in demand, either increase or decrease. If this is delta pd is positive, is increases demand, demand is increased. If delta pd is negative, demand is reduced. Kp is obviously 1 upon b, as we have seen previously. So you can rearrange this expression in a different way. This will be equal to minus delta pd by 1 by kp plus 1 by r. So here and there, that means divide by kp here and here. So it will be 1 upon kp. It will be, this kp will be cancelled out, 1 upon r. 1 upon kp is b, and it is 1 upon r. R is the governor regulation. That means steady state change in frequency delta f static following a change in demand equal to minus delta pd by b plus 1 upon r. B is, as we have previously explained, this is the frequency response of the demand, frequency response of the load or frequency response of the demand. Okay, sometimes this is also called the load damping. Why this is called load damping, I shall explain somewhat later. I shall explain it. This is called load damping, and this obviously is the governor regulation. What is governor regulation? Already we have explained. Okay, governor regulation. Now let us find out the increase in generation. Now if this is the change in frequency, obviously from external you are not changing the position of the speed changer. Some load has been increased by the consumer, they have switched on the load, and that load is being supplied. How? By reducing the frequency of the system. So system frequency decreases, additional load is being supplied. So additional load is being supplied. Where from this additional load is supplied? Obviously there is some increase in generation. Obviously this increase in generation is due to the action of the governor. Governor itself, governor on its own, as already I have mentioned, that this is called the free governor mode of operation. Free governor mode of operation. Okay, governor on its own can actually change the generation. Okay, by sensing the frequency, it can change the generation through throttling effect. Okay, how much is that change in generation? Delta Pg. It is minus del F by R. It is minus del F by R. Okay, why it is minus del F by R? You see that del F by R, delta Pg at steady state, what will happen? It will be minus, if this is 0, this is 0. Delta Pg at steady state, this will be 0, this will be 0. So minus del F at steady state by R. This is delta Pg. Okay. So delta Pg is minus del F by R. You put the value of delta F, it is delta Pd by R into B plus 1 upon R. Or this is equal to delta Pd by 1 plus Br. That means if the demand is changed by the action of the consumer, then generator, because of governor action, and governor is acting on its own, will increase the output of the generation. How much is the increase in that output? It is delta Pd by 1 plus Br. This is the increase in generation due to governor action. And at the same time, what happens? Know that load is sensitive to frequency. Okay, load is sensitive to frequency, and how that frequency sensitivity of the load is expressed, that is by B. B already, if you remember, you see that B was defined here. What is B? Which is del Pd del F. That means how the demand varies with the variation in frequency. That means when the frequency is varied, the components behave in such a manner that they will be demanding a change power from the supply. Some of the loads are there who will consume more power, some other loads will consume less power. Okay. Overall, if we see the total composition of load in a power system, overall response is that with the increase in frequency, demand will increase. That means actual power consumption of the load will increase. With the reduction in frequency, demand of the existing load will decrease. That means existing load, they will actually consume somewhat less power when the frequency decreases. Existing load, they will consume somewhat more power when the frequency is increased. Okay, this is how load actually respond to variation in frequency. So this now, since the frequency is decreasing, the demand of the load also will be changing. It will be load will consume somewhat less power. How much less power? It will be into delta F, because B is del PD del F, means how much is change in demand by the load, that is del PD delta F into delta F. Okay. So it is therefore B delta F. And what is the value of B delta F? We put the value of delta F. It is BR by 1 plus BR into PD. Okay. This is the value of the change in demand, that means reduction in power demand. Okay. So you see that because the load has been changed, frequency, in response to that, frequency has varied, frequency has decreased in response to increase in demand. As a result, in steady state, generator is increasing its power output by delta Pg, that is delta Pd by 1 plus Br. Load is consuming somewhat less power. How much less? It is B delta F equal to Br by 1 plus Br into delta Pd. So if you add up these two, how much is the value? Delta Pg plus B delta F. This is the increase in power demand, and this is the reduction in, this is the increase in generation by the governor action, and this is reduction in power demand of the existing load that are already existing in the system, that is consuming somewhat less power. That is Br by 1 plus Br into delta Pd. If you add these two up, you will have, say, delta Pd into 1 plus Br, here Br by 1 plus Br into delta Pd. If you sum up, it is equal to delta Pd. Okay, that means you see how the increased demand is being supplied by the system. How it is being supplied? It is partly that we are talking about the final steady state. What is happening at the end, when the new steady state is arrived at, after the change in frequency, that means when somebody has switched on a demand, switched on a load, as a result frequency has changed, and as the frequency has changed, what happened? The generator has increased its power output by this amount. Existing load of the system, because the frequency decreases, will be consuming somewhat less power. How much less? It will be consuming this much of power which it was consuming previously. This much will be reduction in power demand by the existing load. So you can see that this reduction in power demand now can be utilized by the new load. So new load will be now getting this much of power. At the same time, new load will be getting this much of power output from the generator. As a result, how much is the total supply of power to the newly connected demand of delta Pd? If you add these two up, it will be equal to delta Pd. So that is how, perhaps this explains how the newly connected load is being supplied by the system. Okay, how the newly connected load is being supplied by the system when a new steady state is reached. So is this clear to you? Anybody, any question here? How the newly connected load is getting power, from where it is getting power? From the system. Is it clear or not? Tell me. বুঝতে পেরেছো everybody?
Yes, sir. Yes.
Okay. Now I shall come to this later on. Okay. Now, can you tell me this? We have actually explained what the newly steady state. But what happens immediately after the load is switched on? Obviously, that load is getting power, is not it? That load is getting power because the load has been switched on. Have you seen the situation such that when you have switched on the fan in your room, the fan was waiting for some time so that power will reach at the end of the fan. It is not like that. As soon as you actually switch on the fan, what happens? Fan starts rotating. That means the fan is getting power immediately after the fan is made on by the action of the switch. So immediately the load is getting power. But increase in generation, it will take some time. Reduction in frequency, it also will take some time. So immediately after the load is switched on, there was no time for the generator rotor to actually change its speed, and then only the frequency will change. So the frequency could not change by that time immediately after that, and therefore the generator could not increase its power output, but the fan is getting power. Where from this fan is getting power? Is the question clear to you? What I want to know from you? Is the question clear to you that when I am making a, I am connecting a load, that means I am making my switch on connected to the fan, fan starts rotating. But by that time, obviously, the time is so short that generator will not get any time to increase its power output because it requires the operation of the governor, because governor operation will be started after the frequency has changed. So there was no time for the frequency to change. But the generator is, but the load is getting power. Where from this load is getting power? That means these two components are absent at that time. Am I clear? Immediately after the load is switched on, this component is not present because delta F was then zero. There is no time for frequency to decrease, and this component was also zero because there was no time for the load to see that frequency has changed. So where from the additional load, where from the fan that I have switched on is getting power? Where from? It is getting power from the stored kinetic energy in the rotor of the generator. Okay. Immediately after you switch on a load, there was no time for the generator to reduce its speed. It will take some time, but by that time, the load will not wait. It will get power. Where from it will get power? Obviously, it will then get power. If we analyze, we can see that the load will then get power from the stored kinetic energy. System has some energy stored in its rotating part, in rotating parts in the rotor of the generator. In the rotor of the generator, there is some energy stored, kinetic energy stored. Okay, in the rotor of all other devices also there are all other rotating machines. There is some energy stored. So therefore, from that stored energy, generator will be delivering power to the load. As a result, immediately after the load is switched on, the load will then get power immediately after the switching operation. The power will come from the stored kinetic energy of the rotor. Okay, is it clear? Stored kinetic energy of the generator rotor. After that, what will happen? After some time, frequency will get, that means the system will get sufficient time. Generator will get sufficient time to reduce its speed. So road speed will start decreasing. As the speed has started decreasing, frequency also will be changing. So frequency has started changing because the generator has started reducing its speed, so frequency has started changing. So as the frequency has changed or it is changing, the governor will now sense that there is a reduction in frequency. So as a result, what will happen? That frequency reduction. So fly balls will actually rotate at a lower speed, and since fibers will rotate at a lower speed, the point B, as we have mentioned previously, will move up, will be pushed up. As a result, because of that section, the generator opening of the steam valve will increase somewhat. So generator will increase its output power. So as the frequency has started decreasing, generator now can deliver more power because of the governor action. Not only that, since the frequency has started changing and started decreasing, existing load also will consume less power, somewhat less power. And these two things, that means changing frequency is in the process of changing, so kinetic energy will be released further. So immediately the power is being supplied by the stored kinetic energy of the system to the load. It is immediate portion. Between after that, before the final steady state is reached, how the power is being supplied to the load. During that time, what happens? Since the frequency is still decreasing, the power will be received from the released kinetic energy by the system. So, since the frequency is changing, the system will reduce its kinetic energy. It will release its kinetic energy. So that released kinetic energy will be actually supplied to the newly connected load, and load will get power from there. Not only that, generator will be generating more power because of the governor action, and load will be consuming less power. Existing load will be consuming less power because of reduced frequency. So during that time, after the initial operation, before the final steady state is reached, between that time, power will be supplied by three components. One is the reducing kinetic energy of the system. Then second is the additional generation by the governor action. Third is the reduction in consumption by the existing load. So these three components will be supplying power to the newly connected load. And finally, when the new steady state has been arrived, then these two components, that means the increased generation and reduced demand of the load, these two will be the sources for power for the newly connected load. And now, after the steady state has been arrived at, you see that there is no further change in frequency. That means no further reduction in the stored kinetic energy. So that component will be absent finally. Okay, so what we can do, we can divide the time starting from the switching on to the final to the arrival of the final steady state. We can divide this time into three different segments. Immediately after the load is switched on, power will be supplied by the stored kinetic energy. After that time, to the arrival of the new steady state, power will be supplied by the reducing kinetic energy, and it will be supplied by the increased generation, and it will be supplied by the reduction in the power demand of the existing load. And finally, when a new steady state has been arrived at, then the power will be supplied solely by the increased generation by the governor action and reduced demand of the existing load. So this is how the power is being supplied to a newly connected load after the switching has been made. We are assuming that we have not changed the position of the speed changer. So because of governor action, governor on its own is changing, doing all these things. Okay. So because of governor action, this is how the load will be supplied by the system. So is it clear? Whatever I have explained, is it clear to you?
Sir, we stored kinetic energy ওইটা proportion.
Which part?
Sir, stored kinetic energy of rotor ওই যেটা একদম শুরু.
Stored kinetic energy. Actually, what happens immediately after the load has been switched on, there was no time for the generator rotor to change its frequency, but there will be a trend of that. So, what is stored kinetic energy? It depends upon the speed of the generator. So if it releases power, how we obtain that power? It is the rate of change of stored kinetic energy. That is the power. So immediately after the load is switched on, what will happen? The impedance of the load is connected to the system. As the impedance of the load is connected to the system, total effective impedance of the system, total effective impedance of the load is changed. As a result, there will be increased current flow from the generator. As there is increased current flow from the generator, So output torque will increase, input torque remains same, output torque increases. So what will happen? There will be a tendency for there will be actually the decelerating force. Because of this decelerating force, so what will happen? The as the speed starts decreasing, speed has not decreased much, but as it starts decreasing, there will be release of kinetic energy by the system, and that kinetic energy alone will be then supplying the power to the load. Generator then cannot increase its power output because before a certain amount of frequency reduction takes place, generator cannot increase its power output because governor will not act. Governor will require that frequency has changed by a certain amount, then only the governor can act. So governor will increase the power output of the generator after a minimum amount of change in frequency has taken place. Okay, but before that time, it is the reduction in stored kinetic energy. Immediately after that, as I explained, the load will appear as an impedance to the system. As the impedance has been changed, so what happened? What is happening? So there is more current delivered. That means current will flow to that load. There will be more current delivered by the system to the output. So output torque to the generator increases. Input torque remains same. So there is some decelerating force acting on the generator. So generator starts decreasing its power output, and as it is doing so, the kinetic energy stored inside the generator decreases, and that kinetic energy is being consumed by the load as the required power. So is it clear?
Yes, sir. Yes.
Okay. Now you see one thing. Let us assume that load is not frequency sensitive. Let us assume that. So if the load is not frequency sensitive, then this part B delta F part would have been absent. Am I clear? If the load is not frequency sensitive, that means the demand of the load does not depend upon frequency. Let us assume that. If this is true, then what will happen? Then B delta F, this part will be zero, is not it? This part will be zero. If this part is zero, then you can say that additional power generation is delta Pg is given by this much only. This that means sum of delta Pg and B delta F. Okay, this obviously is greater than delta Bg itself. So if B delta F this part is zero, what would happen? What could have happened to the frequency of the system? It would have been much more reduced. It would have been reduced by some more amount. Is not that? So if B delta F part were absent, obviously change in the system frequency would have been much higher. Am I clear? Is it clear?
Yes,
Assuming
sir.
that load is not sensitive to frequency, obviously B delta F part will become zero, will remain zero. And if B delta F part remains zero, then you see that the newly connected load is getting somewhat less power to consume. Why somewhat less power to consume? Because existing load, they are consuming the same amount of power that they were consuming previously. So shortfall of generation would have been much higher. Since the shortfall of generation is more, obviously, this shortfall of load would have been supplied by the system by reduce its frequency further. So this frequency sensitivity of the load is therefore called the load damping. Why it is load damping? Because they are acting as a damper to the frequency. They are acting as a damper to the change in frequency. How? Because if load is not sensitive to frequency, frequency would have fallen by a much larger value. This reduction in frequency is there now. Whatever frequency has been reduced, this reduction in frequency is there, but had the load not been responsive to frequency, not been sensitive to frequency, reduction in frequency would have been much higher. So what we can say that as if the load is behaving as a that this particular parameter B, this perhaps is behaving as a damper to the frequency variation. That means when the load increases, frequency decreases. But the frequency reduction is somewhat checked by the by action of this B. Okay. Similarly, had there been some reduction in demand, what would happen? Frequency would have been increased. During that time, because of increase in frequency, what would have happened? Load would have actually been consuming more power. By consuming more power, load as if is reducing the variation in frequency, is putting a brake to the variation in frequency. When the load increases by the action of this B, as if there is a brake applied to the reduction in frequency. Similarly, when the load is reduced by the action of this B, as if there is a brake to the increase in the frequency. That's why this particular parameter B, load damping, it is somewhat some type of frequency sensitive frequency response of the load, or sometimes it is called load damping. It is called load damping because this acts as a brake to the variation in frequency, and this brake obviously is being applied by the load. So is it clear why it is called the load damping?
Yes, sir.
Okay. Now you see that this total at steady state we have arrived at this expression of delta Bg and B delta F. Okay. And we have also explained how the frequency varies or how the load is being supplied to a newly connected load, how the system supplies power to the newly connected load. We have classified or divided the time period by 3 segments, and during each segments, how the power is being supplied by the system to the load, that also we have explained. Now let us see what is the you can say that what is the performance of the speed governing mechanism, how the speed governing mechanism functions in the system. That can be explained by seeing this expression delta Pg and B delta F. And what is the final expression is that delta Pg is del F by minus 1 upon R. And finally, this is the variation in frequency. Steady state frequency is given by minus delta Pd by B plus 1 upon R. Okay. For increased power demand, frequency will decrease. For decreased power demand, frequency will increase. And how the frequency will increase or decrease, that is given by this expression, delta F equal to minus del Pd by B plus 1 upon R. So these characteristics now we can draw here. This is very similar to that what we have done previously for the governor alone. Okay, now it is not the governor alone, it is a total system. Along with the action of the governor, there is the action of the load also. So action of the governor and action of the load, taking everything together, we are getting the frequency response of the total system that we can draw here. Okay, del F here and delta PD here. You see that del F by del PD is minus 1 upon B plus 1 upon R. So minus 1 upon B plus 1 upon R. This is the droop of the system. Okay, previously droop of the governor was somewhat less, it was minus R. Now because of the load and the governor together, this is the droop minus of 1 upon B plus 1 upon R. Okay, so this is the load frequency characteristics of the power system, we can see. Previously whatever we have shown, that was the load frequency characteristics of the governor, and this is the load frequency characteristics of the power system, including the governor action and the behavior of the load. Now you see that, say, during the morning time, say our system is operating at this point. Say this is our demand and this is our frequency. Say now load increases. From here, load has been increased. So what will happen? You see that at steady state, this increase in demand will result in some reduction in frequency, because frequency reduction we have seen at steady state, frequency will fall unless we change the position of the speed changer, frequency will fall. That means governor action alone cannot bring the frequency back to normal value, because any increase in power demand will result in variation in frequency. If the demand decreases, frequency will increase. If the demand increases, frequency will decrease. It is certain to decrease, it is certain to increase following the variation in power demand. Okay, you cannot restrict that. That means governor alone, unless some external effort is made, governor alone cannot control the frequency, cannot bring the frequency back to steady state, to normal value. Governor alone cannot bring the frequency back to normal value. Am I clear? Could you understand this statement? That means, say, if you are installing a speed governor, and if you do not change the speed changer position, that means you are not giving any external input to the speed changer, you are not attempting to change the power generation or change the power output of the generation by changing the position of the speed changer, then what will happen? Because of the variation in demand, because of the variation in load, frequency will vary, you cannot limit it. What most the governor can do, what will happen because of the action of the speed governor and because of the action of the load, it will be somewhat restricted. Frequency variation will be there, it will be somewhat restricted, but you cannot avoid variation in frequency because del F static is given by this one. That means after a load change, frequency cannot be the same as the previous value. It is not possible. So if the situation is like this, what will happen? See, during morning hours, you have fixed the operating frequency for your system. Okay. Now, during morning hours, the load is less. As the day progresses, what happens? Load increases, and because of increased demand, it is certain that frequency will decrease. That means frequency will start decreasing as the demand increases. And if this happens, what will happen to the system frequency? It will vary through a wide range. Okay, through a wide range, frequency will vary. That means frequency control is not there, you can say. In the true sense, frequency control is not there. That means if you depend upon the free governor action alone, then you cannot regulate your frequency, regulate your system frequency. You cannot control your system frequency with the variation in demand. System frequency will be varying. It is bound to vary because governor alone cannot bring the frequency back to normal value. What we have to do to bring the frequency back to normal value? Some input has to be given, and that input has to be given to the speed changer. And that input, when this input is given through the action of the speed changer, then it is said that this is again another control we are applying. This was the primary control. Through the feedback operation of the speed governor, the frequency was somewhat reduced. Frequency variation was somewhat reduced by the speed governor. This is one control. This is the primary control, and this is fast, sufficiently fast. But another control is needed if you want to frequency variation. If you want that frequency variation will not be much, frequency variation will be made zero, then another control is needed. That control is called the supplementary control or secondary control, and that has to be applied through the speed changer. So this is shown like this. Okay, this is shown like this. You see that here it is shown to be minus ki by s. Ki by s. Obviously, can anybody tell me what type of control it is showing here? This particular, you can say that feedback here to the speed changer from the system, it is being taken. Okay, frequency variation is measured, and what type of control is being applied through the speed changer? Can anybody tell me?
Integral control, sir.
Integral control, because it is divided by yourself. And we know that by integral control, if you analyze any integral control, if you want to make the steady state error zero, then it has to be the integral control. Okay, in integral control only, the steady state error is zero. So here also, the speed changer input has to be that type, has to be an integral control. How that integral control will be implemented, that we will see, we will discuss. But through the speed changer, another control input is necessary. and that control is called the supplementary control, or sometimes called the secondary control, because the inner loop is representing the primary control. The outer loop is called the secondary control, okay, or supplementary control, additional, that's why supplementary. Okay, this inner loop is faster because it is done by the speed governor itself, but it requires some external action, and therefore that external action, obviously it is somewhat time consuming. So this outer loop or supplementary control loop is somewhat slower with respect to the primary control. Okay, so this is slower, but this is faster. All right, now let me see how much time is left, so accordingly we shall decide whether we shall be. It is 47. Okay, so shall I continue, or shall I leave it here? Because as you said that some of you are having some laboratory, so what shall I do? Okay, so let me, because that will discussion will require some time, how these actually supplementary control or secondary control will be implemented. That requires some more explanation. That explanation along with some other things, it will be discussing in our next class, therefore, because now it will be taking some time, and that time may not be actually whatever time is left. If I want to leave you at 11:55 according to my clock, then time will not be sufficient. So let us stop here up to this time. Up to here, let us stop here. Next class, I shall explain how the integral control is actually implemented in case of a power system. Not only that, in our country for frequency control, there is a different method. Totally a different method is there. That also I shall explain. I shall discuss in our next class. Okay. So if you are having any question, I shall be answering to that. Otherwise, today, as you have a laboratory, I shall be stopping here. Any question you are having? Anybody? Okay. So if no question is there, let me make the roll call. Abhishek Majumdar,
Present, sir.
then Aditya Rai,
Yes, sir.
then actually Alok some Murmu. I could not actually. Her name is Alak Janri Murmu. Alak Janri Murmu. Miss Murmu. Okay. Then Ali Hamzan,
Present, sir.
Amrita Dotto,
Yes, sir.
Anirudh Anand, Anirudh. Okay. Ankit Jaiswal,
Yes, sir.
Arijit Pal,
Yes, sir.
Arnav Pal,
Yes, sir.
Dipten Mardi,
Yes, sir.
then Dia Rai,
Yes, sir.
Hasibur Rahman, Hasibur Rahman, Konishko Boshak, Kaushik Maji,
Present, sir.
then Manos Patro,
Yes, sir. Yes,
Sandeep
sir.
De,
Yes, sir.
Shankho Mitro,
Yes, sir.
Sayan Banerjee, Shreyas Khatri,
Yes, sir.
Mohammad Soel,
Yes, sir.
Jishan Rahman,
Yes, sir.
Somnath Pal,
Yes, sir.
Pal,
Somnath Pal.
then
Yeah,
Saugato Devnath, Saugato Devnath,
yes, sir. Yes, sir.
Shubhadeep Bera,
Yes, sir.
Shubhadeep Bera,
Yes, sir.
Supratim Nashkar,
Yes, sir.
Surajit Datto, Trina
Yes, sir.
বিশ্বাস,
Yes, sir.
okay,
Yes, sir. Yes, sir.
Trina বিশ্বাস, Ujjwal Haldar,
Yes, sir.
Anybody who could not respond previously, or anybody whose name I could not, or whose name I have missed?
Sir. Sir,
Yeah,
Saurabh
well,
Burman.
Shoudab Burma. Okay, we are present. Anybody else?
Sir, Konishko Vasak.
Konishka Bosha. Okay. So thank you. So Friday again, Friday afternoon we shall be meeting and then we shall be discussing the remaining part. So I expect that next class I shall be in a position to complete the frequency control, and then from next to next we shall be moving towards power system stability. Okay. Thank you.
Thank
Thank you, sir.
you, sir.
Thank you, sir.
Thank you.